This is lab number 3, which many students will miss being able to do because of Easter Monday and Easter Tuesday. So I'm putting it on film. The idea is that you write in your logbook the results that I'm going to give you right now, and you can carry out the lab just like you were here. It's not as good as doing the lab yourself, but it's the best we can do considering we've lost these 2 days to the holiday. Alright, now lab number 3 consists of work which is all using this same box, the same rig, and we have 3 separate parts, part A, part B, part C. Now part A, the first part of the lab, is dealing with this circuit here. Inside the box there is a battery and there's a resistance, and you do not know what size they are. And what you're going to do is you're going to figure out what RT is and VT is by measurement. Now the reason we have the letter T there is because this is what we call the Turbulent voltage and the Turbulent resistance. In that the open circuit voltage you see across A and B is the Turbulent voltage, and the resistance you see looking into A and B is the Turbulent resistance. This is a very important circuit idea. The Turbulent idea is that any circuit, no matter how complicated it is, can be replaced by a single voltage source and a single resistance. So in part A we're going to find out VT and we're going to find out RT. So let's just do part A first. Here is the first thing you have to do, which is simply measure the voltage across the open circuit. So you set the meter up to be volts, and you merely measure what it says, and it says 9.23. So that actually is VT. The open circuit voltage is what you've just measured, 9.23 volts. So we did that. That's the first result of the lab. Now, we've got to figure out what RT is. Now we can't just measure that using the meter because the battery's in the way. If you try and measure that resistance across there, you see the battery's in series, so you can't measure RT directly. So what we do is a different idea. We're going to put a resistance across the voltmeter. And then we're going to change the value of resistance until we see half the original voltage. So you see it was 9.23, and half of that will be about 4.6. So if we reduce the resistance down here, making it smaller and smaller and smaller, eventually the voltage across the AB will reduce. It's already gone down to 8, and now it's down to 7. We're getting there now. What I'm looking for is halfway, which is going to be 4.6. That's 4.7. Alright, so there's 4.6. Let's just take that one down as well. Yeah, about 4.58, very nearly 4.6. Now you might say, why have you done that? Why have you made it half? Well, you see, if the voltage is half, it means the resistance here must be equal to the resistance inside the box. Going back to the circuit, if I put a resistance across there, and I reduce the voltage to half, so I get 4.6 there, and I get 4.6 there. So altogether you can say 4.6 plus 4.6 equals 9.2. If those two voltages are equal, they're dividing the voltage equally. That resistance must be the same as RT. That's why we get half. Half there, half there. They've got to be equal. So that's a result for us. If we read off that resistance there, we know the value of RT, and it's going to be 2,800 ohms. 28 ohms. See? 2 times 1K, 8 times 100. So, RT for this box is 2.8 kiloohms. And that's the result. And that's the end of part A. We've now finished part A of the experiment, the Turbulent theory part. Now we're going to do part B. Part B is where we have 3 terminals and 3 unknown resistors. We don't know what they are. what we're going to do now is again use the multimeter, but this time we're going to go to the ohms range, and we're simply going to measure the resistance across all the combinations. So C to E is 4.4 kiloohms. So across here we got 4.4K. Now we'll go C to D, and we got 5K. Finally, D to E, that's the last combination, and it's 2.7K. Now we've got those numbers, we're in a position where we can find out what's inside the box. Now either inside the box we have this configuration, which is called a star, C, D, E, or we might have inside the box a delta, which is like this. So I'm saying inside the box we could have this one, or we could have this one. We don't know which. No way you can find out which unless you undo the box and have a look. For every one of these, there's an equivalent one of these. That's what I'm saying. Call it RA, RB, and RC. We call this one R1, R2, and R3. Now the best way to go for us is to assume that this is inside the box. Because you see, if we're going to go from, say, C to E, we have to go through RA, then RB. And we can say RCE equals RA plus RB equals 4.4. And then C to D is 5K. And that's, to get from C to D, you have to go through A and then through C. So you go. Equals 5K. And finally, the last one, D to E. And now you're going to have to go through RB and RC. So you've got three equations, and there are three things you don't know, A, B, and C. So you can do your mathematics, your simultaneous equations, and figure out the values of A, B, and C. And you can say to me, if it's a star inside the box, these are the values, A, B, and C. Once you got them, there are formulas on the bottom of your page, on the theory page for this lab, which tell you, if you know those ones, the star, there's a formula to find out the delta. There's a formula for R1, there's a formula for R2, there's a formula for R3, which is given on your book. So what you do in this part B is you measure the resistances, you go through this process to find out RA, RB, and RC, and then you do a conversion from star to delta using the formula which is in your book. Now the last part of the lab is very easy. What you do is you connect this point here to A, take the other way, and this one goes to there. So you see part A is the supplies for part C. And then in the lab, all you've got to do is find the voltage across there, which is VFG. Let's do that in the lab. So I'm going to take the supply from A, part A, and I'm going to connect it to the circuit for part C. Then I'm going to measure the voltage across F and G. So the blue wires are the supply, A feeds part C, and the yellow wires I'm measuring the voltage VFG. And I've got to go to the voltage range, and I'll get my answer. And you see it comes to 177 millivolts. The answer is 177 millivolts in this case. VFG equals 177 millivolts. Now, that's very easy to take that reading, but now what you've got to do is calculate that number using your circuit theorems. So using this circuit, and realizing you still have this resistance in series, you have to use your circuit theories to calculate that value and see if you get the same number. Okay, so that's the end of lab number 3. You do part A, Thevenin, part B, starter delta, and part C, this circuit. Again, it's a bridge circuit where you're going to be measuring the unknown voltage and then calculating it. So you should write all that up in your logbook and make it part of your labs that you hand in at the end of the semester. And that's the end of lab 3.